Hello, everyone, and thank you for joining us today. Welcome to Mega's special webinar series. Today's topic is understanding proactive cable maintenance programs and the testing behind them. My name is Michael Fleischer, and I'm the digital marketing specialist for Mega. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenters today are Darren Byrne, Director of Systems and Services, as well as Charles Nybeck, Applications Engineer. To assist with our question and answer session, we will have joining us Gallo Turan, Cable Segment Manager, as well as Leiloni Vidal, Account Manager for Cable Services. All right, let's get started. I'll send this over to Darren Byrne to kick us off. Thank you so much for joining in today, Darren.
Thank you so much, Michael. We really appreciate it, and we appreciate everybody joining the call today, so thank you. So, as Michael said, we're going to be talking today on understanding proactive cable maintenance programs and the testing behind them. But we're going to get into a lot of different topics here. We're not just going to think about cable testing and the technology behind what identifies cable failure modes. We're going to think about cable life and performance to extend the cable asset life. And this is going to be presented by myself and Charles Nybeck, my colleague. So without further ado, the agenda is going to be cable asset performance management. We're going to get into some failure mechanisms within medium voltage cables. We're going to talk about the test and diagnostic tools to detect those failures, what service types that we offer, what to expect, and then we'll get into some frequently asked questions as well. So as I said, this is not just about testing cables. This is about making decisions on those assets for our customers and our partners. So it's going to be those beginning of life issues, those commissioning. Let's talk about, say, wind farms or solar or new feeder commissioning. Being able to predict end of life, so decision-making process to repair or replace or just to simply leave in the ground as like new cables, and really get into useful asset life to maximize asset return, if you will. So what we're trying to do here is give our customers insight into their cable systems. If you think about underground systems, they're generally hard to evaluate. They're not like overhead where you can actually look at the condition. These are hard to evaluate just because of their inherent concealment. And really, even if we had all the money available to us to replace aging systems, we don't have the human resources to do that job necessarily. So we're going to look at technology solutions to deal with these assets. So we're going to give you insight into the cables, into your cable systems. Basically to identify those components of the cable system that are healthy. So when we think cable system, we think the terminations, we think splices, and we think the cable itself. We're going to be able to tell you what of those components could be repaired, what system should be replaced based on how severe the issues are, and really more importantly, when these components should be rehabilitated, maybe using some rudimentary risk of failure modeling, just to get to the benefits to optimize resources. As I said, that could be human resources, it could be just project time to complete a project. We want to improve reliability, so bring the reliability indices to manageable levels. So whatever key performance indicators that you're looking at, whether it's customer minutes of interruption or SAFE or CAFE, to bring those in line to where they're manageable. We want to help you reduce your O&M spend so you have less unplanned outages, which is of course going to reduce O&M expenses. And we want to show you how you're going to increase capital reach. Since some cables are going to assess as defect free or as good as new, then we're able to increase asset return or capital reach, and we'll get into that. So what I'm going to do right now is hand it over to Charles Nybeck, my colleague, who's going to talk about failure mechanisms in medium voltage cables and those tools to test and diagnose those cable systems. So Charles, I'm going to hand it over to you right now. Thanks, Charles.
Thank you very much, Darren. I appreciate the introduction. And thank you everybody for joining us today. Hope you're having a good day. So as Darren had mentioned, medium voltage cables are suspect to damage, defects, and issues that can be inherent from several different incidences. And first, we're going to take a look at some local issues that can be found in either the joint or the termination. So if we look into those issues, we can see that these are typically going to be workmanship issues. And the reason being is, if you think about it, the person that installs these splices, these joints, or these terminations are people. And although they didn't mean to, sometimes people accidentally make mistakes. That could be uneven cutbacks. That could be, sanding wrong. So there can be some mistakes that are made, cuts into the insulation, what have you. And although they seem small at the time, when in service and over a period of time of aging and deterioration, they can lead to a failure. If we look at the termination, we can see a failure in the termination. And if we look at the splice or the joint over here, we can also see some obvious tracking, discharges, and ultimately some a defect there as well. Next is another local issue, but this is weak spots in the actual installation of the cable. And there's several different reasons for this as well. One could be manufacturer defects, which over time can lead to electrical trees within your cable, which we all know is it's a very bad defect to have. So, we want to make sure that we check for those. Another one is a small bending radius. So these medium voltage cables have a rated bending radius. If you exceed that bending radius, you could damage that cable permanently. It could have an inhomogeneous field distribution then at that point, and can cause some field concentrations, and then therefore some defects, maybe even some partial discharge at that point. So we really want to make sure that we avoid these local weak spots in the insulation as well. Lastly, we have the insulation global issue. Now, by global, we mean all encompassing, like the whole cable. So this is an integral measurement, and I'll get into this a little bit more on a later slide. But this global issue can be things such as water tree ingress due to just kind of natural aging, or subject to moisture, as well as the cellulose degradation within the insulation as well. Here we wanted to take an example to look at some specific local problems that we found, where first we have an example of a transmission cable here. I know the focus is medium voltage cable, and we'll get right back to it, but I just wanted to show an example of a defect or some damage that could be done by installation or through transportation. Now next, we do have a medium voltage cable here, where you can see that we have a heat shrink splice, and that splice wasn't heated all the way to be totally uniform or connected to the cable there, the insulation there. And if we look, we can actually see resulted tracking, and you can see that the cavity that's created there, partial discharge activity taking place, and you can actually see that tracking on the cable itself there, that insulation. Next is a example of clamping a cable. So you just have a cable clamp to hold the cable in place. Now these are supposed to be specified to a certain torque. You shouldn't over torque these to cause damage. Now in this case, what had happened was that there was too much force put on these and ended up causing damage to the cable. If we look, we can see all three cables were over torqued and therefore permanently damaging the cables. And similar to the bend radius, what that's going to do is it can affect the field, the electrical field distribution at that point, and again is a prime point to have some partial discharges or other defects taking place. And that's going to be kind of in the main insulation, obviously, between any of your splices or terminations there. Finally, we have an example of what happens whenever these defects are not really, there's not action taken on these defects. As we mentioned before, these defects, they start out as defects, right? But over time, they can lead to a failure. And in this case, at the termination of this cable, we can see a failure. I mean, it's the result is that there's ash blown all over the side of the building there. So catastrophic failure there, as well as in this next example here, we can see another severe failure as well. And the issue is with these is not only do you have to replace what was damaged, but you also have to deal with the cost of an unscheduled outage in this case as well. So the question is what can we do to stop these defects or determine that there's defects and then take corrective action so that way we don't get those failures, right? So here we have a list of 3 test and diagnostic tools that can be used to do exactly that. The first is VLF, or very low frequency. VLF is a simple, non-destructive withstand test that can be performed. So similar to a high pot, only performed at 0.1 hertz and non-destructive. And the beauty of this test is it provides a very clear pass or fail result where there's not any need for interpretation. What I mean is if you perform a VLF test and you pass, you apply your VLF withstand for 30 or 60 minutes, and if you pass, you have no failure. I mean, right? So it's very clear. Now, if you do have a failure, it's going to tell you you're essentially driving a defect in that cable to failure, and therefore the test will indicate that you have a failure. Now, this sounds negative. It sounds bad, right? Because you failed the cable. But if you really stop and think about it, you took a defect that was close to failure, and during a planned outage and testing, you drove it to a failure, and now you have the means to locate the fault through some fault location equipment, make the repair, and then put the cable back in service, back close to that like new condition, with the peace of mind that that defect that was close to failure is now identified and repaired. Now, another valuable tool is tan delta here. And tan delta is a measurement into the cable's insulation or dielectric strength. This is an integral measurement, and what that means is it's a global measurement. So if we think back to the failure mechanism slide and we think of the global issues, this is a measurement that will help us to understand if there's the presence of water trees or cellulose degradation, and give us really the overall condition assessment of that cable insulation. And through the IEEE 400.2, we can actually get immediate field results as to whether or not there needs to be action to take, action required or no action required, or even further study into the cable. And tan delta is a non-destructive measurement, won't stress your cable. So once the cable is confirmed to pass or has a confirmed good measurement, the cable can be put back in service and with peace of mind. Now, the last one we have here is partial discharge. And partial discharge gives you the ability to detect developing defects before they occur. What that means is you have a chance to find defects at an earlier stage, right? So before they become a real issue or lead to a fault. Also, partial discharge is often used to verify workmanship issues. So if you had splices or terminations that were redone on a cable, partial discharge testing is a good test to do to verify that that was done correctly. Now, partial discharge can also identify or testing for partial discharge can identify whether or not you have PD activity that's occurring while the cable's in service. And the way you do this is determining the PD-IV and the PD-EV, which is the partial discharge inception voltage and partial discharge extinction voltage, respectively. And I'm not going to get into great detail, but the thing is if both of those values, the PD-IV and EV, are above your operating voltage, then you can have good peace of mind that you're not going to have partial discharge activity while the cable's in service. And there's more than just the black and white case, but this is more or less the case. And if you have your partial discharge inception and extinction voltage below the operating voltage, this is a completely different story. That means that despite the situation, you're going to have partial discharge taking place within that cable, and it's eventually going to lead to a failure. Also, if you have an experience analysis of your partial discharge testing, you can use this as the basis for your further assertive decisions. So again, really the 3 test and diagnostic tools that are strong for determining the condition of your cable here. Next, we'll take a look at the service types that can be provided by using these 3 test and diagnostic tools. And this can cover commissioning, acceptance, or maintenance testing. If we look at the far left picture, we can see we have the complete picture by using the 3 tests, the VLF, tan delta, and PD. That means we can find the global assessment of the cable, so we can determine the overall health of the installation. We can run partial discharge tests to determine if there's any issues within our accessories, our splices, or our joints or terminations, and if there's any weak spots that are being identified. And then with VLF, we can drive those weak spots to a failure. We can repair them and then you have the complete picture, and you have all of things on the table to perform any service or any repairs that you want to do. Next, in the middle, we have the condition assessment of service age cable, which you can notice involves PD and tan delta, and we're missing the VLF. So in this case, we have tan delta, which gives us the global or overall assessment into the condition of the cable. And we have partial discharge testing that allows us to assess the accessories such as the joints, splices, and terminations, as well as maybe even find some of the weak spots in the cable. You really kind of want to shy away from VLF in this situation because it's service stage cable, and you don't really want to add unwanted stress to the cable if not necessary. Now, in the terms of the right, we have the commission and acceptance testing, which involves partial discharge and VLF, and you'll notice tan delta is missing. And the fact is that through partial discharge, again, you can verify the accessories. Through VLF, you can determine that there were no gross defects during the manufacturing process that may lead to a failure. But tan delta is not really recommended in this case because the cable still has some of the chemical processes taking place that are going to influence that dielectric measurement, and won't really be a representative tan delta measurement. So you really want to wait some time while that cable is in service to let those processes take place, settle, before you perform your tan delta measurement, as if you performed it on a commission test, it really provides no value in trending or any measurement moving forward. Now, if we start to take a look at these individually, we can take a look at the complete picture here. And as I had mentioned earlier, with the complete picture with PD, tan delta, and VLF, we have the ability to not only determine the global condition of the cable insulation, but we can now look at the joints and terminations through partial discharge, as well as weak spots. And then we can, with VLF, we can drive any of those weak spots that are close to failure, and then have the chance to do those repairs while in that outage, that planned outage, as you don't have the failure or the defect driven to a failure while in service, causing an unplanned outage. If we look at the condition assessment of service stage cable, again, kind of just visually showing what I said earlier, we can determine the global condition assessment of the insulation of the cable, and as well as still with the partial discharge, we can determine the condition of the joints, splices, and terminations to determine that there were no workmanship errors that may lead to a defect in the future. Now you can see the weak spot is X'd out, but in reality, we can find mid-span PD activity in the insulation between joints or splices or terminations. And one situation may be similar to, and I'll call upon this again because we're going to kind of look at a measurement example that could show something similar, but it could be the overclamping of those cables or the bend radius exceeding that bend radius. So that could be a situation where you may find mid-span PD and find a local weak spot. Then we have our commission acceptance testing. So again, through partial discharge testing, we're able to find any issues, workmanship issues in our joints, splices, or our terminations, as well as any localized weak spots in the installation that may be due to the manufacturing defects or the way it was handled. Now, since we don't have tan delta being performed here, we don't really get the global assessment of the installation condition. But if you think about it, from the manufacturing process, there shouldn't be any cellulose degradation. Should be no water trees if it was handled and transported correctly. So that tan delta measurement, again, is not really going to be consequential in this case. Now here we have an example of the PD Detector software. And so really what I wanted to do here was just kind of step you through the software for doing a partial discharge measurement, just kind of give you a visualization of what may happen. Where here we have the home screen, if you will, of the PD Detector software with the library up top, where you can have your cable number, the location of the cable, your station A and B, so near end and far end, and you can swap those so you don't have to rebuild the cable later. The length and meters, as well as your RMS voltage, so you can kind of see all of that, and that's all of your header information. If you move forward, you see you have the pinwheel, classic pinwheel design here, where it steps you through each process. But really, if we look, we can see we've built the cable, and that's the real thing. We have station A, we have about 1,020 meters of cable. You can see a splice indicated by the gray bars there, another stretch of cable with another splice, and then finally a small stretch of cable to station B. And here we have a classic example of a calibration of a cable. So here in this case, we're injecting 1 nanocoulomb. And that can be seen at the very bottom where you see the periodic spikes. Those are actually the injection of the calibration signal. And then that thick bar of black at the very bottom is actually the background noise. So you can see that it provides a very good signal to noise ratio there. And there's actually a screen past this, we don't show it, but it's the disturbance level where you can actually quantify the background noise. If we look at the top, you can actually see the calibration itself where we have a very strong signal on the near end. You can see the very first splice there. A little bit after, you can see the second splice, and then just after the second splice, you can see the nice reflection from the far end of the cable. So here we have an example of an actual partial discharge measurement using the damped AC or DAC waveform. So we have capability of performing partial discharge testing using several different waveforms, ranging from cosine rectangular to VLF sinus to damped AC. This is an example of a damped AC waveform. You can see at the very top as it decays over time. And at the very bottom, we can see that we have partial discharge measurements, but not only do we have the measurements, but we have them localized as well. So you can actually see lines 1 or phase 1 and 2 indicated by the blue triangle and the yellow or orange square respectively. We can see that the localization shows that that partial discharge activity is taking place at that splice, which is indicated by the dotted line at that 100-meter mark. So again, just kind of showing the fact that we can not only determine local if we have PD activity, but also localize it to where in the cable are we actually seeing that. We also have another example here where we have several different sources of partial discharge. So we can see partial discharge at the splice in the middle, indicated by phase 2. But if we look kind of to the right and left, we see some other, kind of mid-span PD activity. And that was what I was talking about earlier, finding partial discharge in the between the splices, which is in the very middle there, and towards the right at about just over 900 meters there. So we can see that between those two, we have PD activity on phase 1, 2, and 3. And the situation like this, as I go right back to that cable clamping, is if those cables were clamped and over torqued, then you can cause that inhomogeneous distribution of field and cause PD activity to take place. And it was done on all 3 phases. So this is something that could be representative of a condition like that, where you may cause a defect by over torquing your cable. This is the same measurement, but just shows the damped AC applied wave on the bottom. And those blue spikes you see coming up on the first waveform is, or the first period of the waveform, is actually the partial discharge taking place. So that's the partial discharge, then it takes it and it maps it and localizes it for you in the above graph there with the PD level and the distance at which the partial discharge is taking place. So again, just wanted to show an example of kind of what a partial discharge measurement would look like. So here is an example of what to expect with an in-depth consultation to determine the overall scope of your application, which in this case is a cable replacement project. And the measurement method in this case would likely be tan delta and partial discharge, in which the 3-step process would be to first safely de-energize the cable. Second, we'd connect the tan delta unit and take our measurement. This is approximately 5 to 10 minutes here. And then third, we would do our field evaluation of the tan delta results, which we saw earlier is done by the instrument and gives us back whether or not action needs to be taken, no action can be taken, or further investigation. So if the cable passes, we can then perform partial discharge measurements and verify that the accessories for defects. So now that we know the overall condition of the cable is good, we can then look at the splices and terminations individually, determine if they need to be replaced or what have you. If the cable fails the tan delta, then we can simply move on because we already know that the overall condition assessment of that cable has failed. After the evaluation, we'll do our post-test evaluation and then generate our final report with our findings. So just a very simple process and to the cable replacement plan there. Here, just kind of wanted to show an example of kind of our test instrument and setup. Expediency is always an issue with this, so just kind of wanted to show you the simplicity, where in this case we have a TDM45 with the base module and boost module capable of performing tan delta, VLF, and PD with those three waveforms or wave shapes that I had mentioned, the damped AC, cosine rectangular, and VLF sinus. Where first connection that we need to make is just our ground connection, interconnecting the units into the station ground. Next is our control unit from the boost to the base module. Then we have our input power, and then finally our high voltage that interconnects the two units and then to the cable under test. So you can see 4 connections, very straightforward. Now we're ready to perform both VLF and tan delta measurements. In the next case I wanted to show you is the TDM45 in the case of partial discharge. You can see that there's a few more accessories here, but once we step through, you'll really see how easy it is to set this up as well, where again, our first connection is going to be our ground connection. Second will be our input power to both the unit as well as the communication box. Next, we have our comms from the unit and through the PC that controls our PD detector software that we saw on the previous slide. Next would be the trigger. That's for the boost module to the comms unit for our partial discharge measurement. And then you have communications to the PDS60, which is your partial discharge coupler. So that has your reference capacitor, your coupling capacitor, and your conditioning electronics. And then finally, last but not least, our high voltage cable leading to the PDS and then to the device under test. Unless the capacitance of the cable is low, and in which case we would add a support capacitor that would be between the test system and the PD coupler. So again, very straightforward, simple measurement, but what you may more likely see is actually the next case. And in this case, we have all of these into a compact test van. So now not only do you have the capability that we just showed you, but you have cable fault capability. So if you were to run a VLF, you could simply run your cable fault afterward. And this is all, again, in one compact design in a test van that's designed to do this. So you can see on the left, you have some cable fault equipment. You have your command center, your control center there. You can see the woman on the left that's controlling it with the classic pinwheel turn knob. It's touchscreen computer, runs on the Linux system. So again, fully complete to run all the tests. And if we actually look at the back of the van, we can actually see the TDM45 actually labeled there. You can see the high voltage cable being pulled out. You have your grounding cables, your communication cables. You even have on the bottom of the drawers there some accessories that come with the van as well. So that'll be including the diagnostic set as seen on the left here. And then some additional accessories as well as some safety features such as a grounding rod for to check your ground, the condition of your ground, as well as the status of the test and your e-stop. So again, you know, you may have this, just the simple TDM system, or you may have the full cable system that's capable of all of your test and diagnostics as well as cable fault location and one convenient, unique compact design there. So here we wanted to take an example of to show you some field results and some memory, just kind of a classic example of a tan delta measurement. So this is kind of what I was talking about earlier as to the assessment of tan delta after the test is performed. We can see in accordance to the IEEE 400.2. And in this case, there was action required on all 3 phases, but there's 3 possibilities of no action required, further study advised, or action required. So you get immediate results and recommendations there. And the other thing is that the internal memory stores these measurements for your reporting. So while in on-site testing, that's all you need to focus on. You run your test, you move to the next test, you run your test. Afterward, we can pull all the data for our final reporting. And speaking of reporting, here's an example of some reports. On the left, we can see an example of a fault that's found at 220 meters. You can see that on the bottom on the cable diagram on phase 1. You can see at 220 meters, we have a fault, so it actually indicates that for you. If we look at the top on the left, we have our header information. On the right, you actually have a geographical mapping of that cable with an actual, localized map, and shows you the defect there as well. So comprehensive reporting capabilities. And on the right, if we look and we see we have the analysis. So we have the charts, the measurement data, as well as recommended action. In this case, a tan delta measurement was performed. We can see at 9.4 kV, the frequency, the voltage steps, as well as the results of the measurement and some of the statistics that were determined there, as well as the result giving us the recommendation.
Well, thank you, Charles. I appreciate you explaining all of that. And I'm going to take over right now and get into the managed cable services part of the presentation, which is going to discuss the operations and the decision-making process. So just to start off here, I want to say that utilities are faced not only with aging assets, they also have an aging workforce. So we know that they need technology to help them manage and extend cable asset life. If we look at the United States alone, there's 6 million miles of power distribution systems and 18% are buried underground. And many of these assets are at the end of their life expectancies. So we know that utilities have difficult decisions to make, whether it's to just run to failure or it's replace complete loops based on age and failure rate. They're definitely dealing with deteriorating asset performance. So what we're going to show in this part of the presentation is some effective solutions to be proactive, to save money, to save time, and prevent basically power outages. We already said at the beginning that even if the utilities had all the money, all the budget, they still don't necessarily have the resources to deal with their aging infrastructure. So it's going to take a technology approach. So what drives this? Basically, as we read about the utilities, grid hardening and modernization is at the forefront. We know there's government regulations in terms of the reliability indices and the key performance indicators around safety and KD and SAIDI, etc., customer minutes of interruption. So what we're looking to do is help our customers verify the integrity of their power systems to increase that reliability. And there's two ways you can do this. With new assets, we can offer cable commissioning and acceptance testing. And this is mostly project type work where we would maybe help you verify the integrity of new feeders or the cables at a wind or solar farm, and certainly at critical facilities. And typically this is an insurance policy at the beginning of life for that cable, that it's as you get the defects out of a new system, it's going to have a major influence on asset lifetime performance, and it's going to help you maximize your investment return. And typically these types of engagements are pretty low. In contrast, we also want to look at the other end of the continuum, which is a cable life extension program. And this is those age type assets. They've been in the ground for quite a while. In some cases, they could be at end of life. They've been fully depreciated. And basically, it's program type work, where based on your scope, and your scope could be, hey, we're having problems in our scope where 80% of our issues are coming from 20% of our installed base. So that could be, some older cables pre-1985, for example, cables that are 35, 40 years old, fully depreciated, and reliability needs improving in this area. But this would be then an alternative to wholesale replacement. You're only going to rehabilitate those cables that are non-passing, that they don't pass the test. So this is more of a value-based opportunity, more than an insurance policy. This is going to help you just deal and make proactive decisions on, as I said, only those cables that have defects. So we're going to have a focus in these cases of reliability improvement. We're going to look at extending capital, and as I said, proactive replacement, reliability improvement is also going to reduce your O&M spend. So again, looking to avoid those unplanned outages and maximize asset return. In this type of engagement, if you have a scope of cable where, I've seen 10,000 miles falling into a scope of pre-1985 cable, unjacketed cable. It depends on how many cable test fans you want to throw at it, the solution, which we're going to help you, and we have calculators to do this that are online that I'll get into. But this is all going to be dependent on scope. This is not just about testing one cable, it's looking at testing whole populations of cables. So we'll get into that a little bit more. So what do you need from us as our prospects or our customers? You need high quality, you need reliability. So you need to be able to trust the results. So you need reliable asset condition analysis. You're going to need some form of consultation. So you're going to rely on maybe our expertise and advice on solutions in terms of newly installed systems and even what's going on with your aging systems. And it's got to be cost effective to optimize resources. That could be your capital resources and your human resources. So I look at this in terms of 4 pillars. What we want to do is choose the right technology. So we want to optimize the technology. So Charles touched upon it. We have the complete picture in terms of partial discharge, withstand, and tangent delta or tan delta testing. But the issue here is not just to be accurate. We have to be efficient and integrated into your systems. In other words, we could, if we're only testing 1 cable a day with a cable test van, then we're not efficient. So what we have to be is testing 5, 6 cables a day. So it's not just about choosing the right technology, it's also being accurate and efficient and integrated into your systems. So that's the second part, is system design and integration. Supplying a complete solution and integrating it into your OMS system, your outage management system, your GIS, or your asset management system, and maybe even possibly taking responsibility for the actual rehabilitation of those cables that don't pass the test, but certainly giving you some form of consultancy there. Offering innovative services to just apply the technology wherever you are, and even get into predictive life of the asset using artificial intelligence and machine learning, looking at margin of clearance of over operating voltage in terms of partial discharge, how severe is the issue, looking at phase patterns and using phase pattern recognition, but really coming up with these innovative services so that we can help you predict asset life, and then consulting with you, making sure that we're not just supplying you with the product, we're actually supplying you with asset and process consultancy. So even if there's people that are attending or companies that are attending this presentation right now, if you have our equipment, we're willing to come out and consult with you on that equipment. Maybe you're looking at starting a life extension program. We can send consultants out and work with you for a week or 2 or a month on how you might start up an asset management program. So that's something to bear in mind. And this slide is just basically showing asset life cycle. When should you test? Probably everybody on the call is familiar with the bathtub curve, which is in the lower right-hand side of the screen here, where it starts out at infant mortality. This is your startup commissioning, and then you have a period of useful life, and then your asset wears out. This is exactly the same with cable. At the end there, over time, you have a fully depreciated asset that's written off the books. So we can actually do quality control testing. This is that commissioning or acceptance testing, minimizing the risk of failure on new installs by identifying those craftsmanship issues, manufacturing defects. It could be shipping and handling, but basically looking to extend the life of that new asset. And then having regular maintenance throughout the useful life period, maximizing the cable system reliability and asset life by detecting and eradicating defects. And then extending the life with having a proactive asset management solution of aged medium voltage cables, where you can optimize capital investments and optimize reach of your budget to extend the life of those assets. And we're going to get into that as we move forward here. So what can you expect after the cable is de-energized? What we've done here is we want to show you just a loop here, and just for expediency, I've just shown a loop here of 6 cables from riser to riser, going through the neighborhood. And what you can expect here is, what we're going to do is, we're going to set up with the van at the first transformer here, and we're going to conduct the first test from transformer to riser. We're going to identify any issues of terminations because they're above ground, and remediate any that have any discharge right there. So we're going to initially remediate any issues right away with any termination issues that we see. That's those local issues that Charles had mentioned in the first part of this presentation. Then we're going to retest if that happens. While we're there, and if we're at the normal open point, we're going to check for arrestor protection and install it if needed. We're going to report transformer condition. That could be if we see a leaking bushing, for example. We're going to report it. If we see that the pad mount has subsided or it's crumbling, then we might as well report that. That's typical O&M maintenance, but why not report it right here, because we're at the asset anyway. So this is ancillary information, if you will. We're going to report then any midspan defects or at an in the installation or within a splice. And if midspan defects are found, then we're going to follow up with we're going to have you follow up with rehabilitation crews that will repair or replace that cable based on a risk of failure analysis. And then we're going to move to the next cable, as you see here. This time we're going transformer to transformer in assessment 2. Assessment 3 is transformer to transformer at the open point there, which could get moved, or you could take a full outage for the neighborhood. Assessment 4 is then, assessment 5 is then taken, assessment 6. So that's typically a day's worth of work in assessing cables with a cable test van. So let's look at this in terms of asset management solutions now. If we're the asset manager and we're looking to extend the life of our current system using this proactive approach, only dealing with those cables that have the defects. So again, using the same loop here, we're looking at the 6 cable segments. Just for example's sake here, I'm showing that each cable segment is approximately 350 feet long. So, and the replacement cost is about $100 per foot, which is not out of the realm of possibility, by the way, looking at an all-in cost of $100 per foot to replace cable. And this is why we say this is an expensive proposition. If those cables that are in the ground are passing these tests, then nothing more needs to be done to them. So you're basically, they're like new cables. Going back to the example here, we have the entire loop of 6 cables, 6 spans basically, times 350 feet, times $100 a foot replacement. That would come to $210,000 to replace this whole loop. So the asset right here, if we look at the loop as the asset, it's $210,000. And the reason why I like to look at the loop itself, because the loop really is as strong as its weakest link, or in this particular case, it's as strong as its weakest link in the half loop or the radial. So each cable span here is worth $35,000. That's 6 times 35 is $210,000. And then just to finish up the example here, the test costs, let's say roughly $1,500, and the repair cost of anything that we might repair is about $5,000. That's to maybe repair a termination at the time of the test. And I might be high with some of the numbers, but I want to show these numbers so that you can see how the life extension program works. So let's start at assessment 1. Here we can see assessment 1. It's now marked in green. That means if we look in the table, the asset's $35,000. The test cost $1,500. Therefore, you've saved $33,500 immediately. All you've spent on this particular asset that is defect-free is $1,500 to test it. The second assessment now comes back green, so we've got the same exact inputs in the table. We've saved $33,500, or we've saved about $67,000 with our second test. Now, in contrast, the third test, we see here it's in red. There's so many issues mid-span that this cable should most likely be replaced. And as we look at the cable, table, we can see assessment 3. Typically to replace it is $35,000. However, we did test it and we've got to replace it, that means we're negative $1,500 on this test right now if we're comparing to wholesale replacement. Test number 4, we believe that this should be repaired. So again, we've got the $1,500 to test it, identify where the issues are. We've repaired it for $5,000. So now we have a net savings here over wholesale replacement of $28,500. The next cable passes, exactly the same we can see in number 5. The next cable fails, we look at the table, and it's exactly the same as the assessment number 3 that failed, that were negative $1,500. But if we add everything up right here, wholesale replacement would have cost us $210,000. We spent approximately $9,000 on tests for this day. We had one cable that needed replacing in assessment 4, and we had one cable that needed repairing at $5,000. That's assessment 4, and then 2 cables that needed replacing. So all in all, we've spent $70,000 plus $5,000, that's $75,000, plus the 9 to test it, about $84,000. So what's actually happened here is we've got the whole loop back to a defect-free condition, but we've only spent $84,000 versus $210,000. So we've actually extended budget reach right now for this loop by 2.5 times, which means we can go and assess another 1.5 loops, and with the same budget that it would cost to test just the one loop. So we've got 2.5 loops basically in all. So we've saved $126,000. And that's actually given us a return of $14 for every dollar that was invested, since 9 into 126 goes about 14 times. So this is what we're talking about in terms of the economics. But think about everything else that we've also done here. We're actually doing more with less. So project management, there's efficiency here. You're only replacing 2 cables and repairing 1, whereas a wholesale replacement approach would have taken would have required to replace all 6 cables. So there's project management. You're gonna finish a project quicker, 2.5 times quicker. Resource utilization. If a utility can bore in just a certain amount of cable per day, then in this particular case, in the proactive solution, you're only boring in 2 cables versus 6. So we're saving time with crew days and crew costs. We've got the investment return there, $14 for every dollar invested. But the main thing that's going to happen here is, because we've got the same result, a defect-free cable system, we're going to improve the reliability of the whole system. So now let's look at risk assessment and rehabilitation priority. So now we've got all the results, and as Charles was showing, that we have the results that can be uploaded into your systems, your asset management systems. We talked about having the complete picture. We then talked about risk and health assessment, which is what we're getting into now, and asset condition. So what the structure information look like. We can actually look at leaking bushings, at transformers, and report them, as I mentioned before, if the arrestor's in place. If it's not there, then maybe it should be put in there. But basically, we're looking at risk of failure, and also the probability of failure. So it's the probability of failure. Risk is the probability of failure multiplied by the impact of failure. This means that the total amount of risk exposure is the probability of, let's say, the fault occurring multiplied by the potential impact or the damage incurred by the event. And that impact could be financial in terms of customer interruption costs. You certainly got replacement decisions, and you've probably got some collateral damage costs that are financial. We talked about reliability indices, SAFE, SAIDI, CAIDI, CMI. That's all gets affected, and that has an impact to the utility. We talked about criticality. Sorry, I can't say it. Hospitals, major venues, data centers, petrochemical plants, airports. There's a big impact of failure if a cable fails and takes them out. And then also environmental. We've certainly heard a lot about fire risks, and we've heard about environmental oil leaks and the like. So we're looking at probability times impact as we look at risk. And we can model that in a rudimentary type of way, whereas as we look at the y-axis here, this is that probability or likelihood of failure. This is that risk that we talked about, where we can see here in the bottom left-hand side, we've got like a low probability and a low risk, a low risk of failure. So how do we determine this risk? Well, as we look at the top row here along the x-axis, we can see what might constitute a cable with a high risk of failure. Remember, we're looking at defects. Well, a poor neutral could contribute to it. We could see a partial discharge defect at operating voltage, or the cable could have been so close to failure that it could have faulted under test. So these are what we would call very high risk or very high probability or likelihood of failure type cables. And as we look at the next row, we might see joint and termination defects at operating voltage. Now, these types of defects, the components versus the insulation, the cable insulation, the components are usually much more resilient. So they still have a high risk of failure, but not as high as if the issue was in the insulation itself. So these may require, these are high risk of failure, so they should probably be looked at within the next, I don't know, month or so, months to 3 months. Then medium risk, defects above operating voltage, or low risk, those are those passing cable systems where possibly the arrestor wasn't in place. So we're not clipping any of those transients that are out there, such as lightning transients or switching events and the like. So that's looking at that risk of failure, the likelihood of failure. But as we look along the x-axis here, we can see an impact of failure. So this is that this is what we're talking about in terms of two cables could have exactly the same issues, but one, as we look at the top right of this particular matrix, one feeds a trendy downtown neighborhood. So there's an impact of customer minutes interrupted, whereas to the other end, again, it's the same issue, but it's less impact. It's maybe a parking lot in a rural area somewhere. So again, same risk of failure, but not the same impact of failure. So this is what we want to do, is work with you in terms of that improvement, by working with you on how to determine how you would rehabilitate your cable systems and the like. And let's move on, so that we can basically give you the precise condition of all the assets. We can give it to you on a loop by loop basis, ensure that the system is defect free, extend the life of aged assets, increase budget reach, reduce failures, and make sure that it's faster than replacement. So your expected outcomes are going to be increased uptime, decreased maintenance cost. You're going to have you're going to improve your capital reach, as we showed in the example, 2.5 times. Improve resource utilization, that your crews and crew days required to replace only those cables that require some form of rehabilitation, only those are touched. So you're actually improving resource utilization. And then looking at the impact model, you know where to send those crews first, based on risk and impact of failure. So looking to extend the life of your cable system. So why choose Mega as the service provider? So we have over 130 years of experience in the electrical testing industry. And that means we've been in the industry for a long time. We're a proven leader. And we already work side by side with probably most every person that's on the phone, or every company that's on the call today. We also have premier test equipment. So they provide thorough and exhaustive diagnostic analysis of the assets, allowing us to find the defects in your cable systems that maybe others can't. And we also have OEM knowledge. We manufacture this equipment. We actually sell the equipment, and not just the service. So we're able to get more out of our test units and provide better and maybe more reliable asset management results. So you truly are partnering with a proven leader. So this, I believe, is my last slide. I just wanted to just stimulate some gray matter as we go into a question and answer session right now. When you think about your program, what are you looking to do? What's the precise definition of the problem that you're hoping to address? Is it extend the life of aged assets? Is it commissioning new installs? Is it a little of both? Do you know your scope, what your problem scope is? Is it 1,000 miles? Is it just 50 miles? How are you currently dealing with the issue? Are you currently dealing with it? Are you running a run to failure approach? Or do you have a budget? Do you know your failure rate? Do you know how fast you want to fix the problem? Do you have a reliability metric, and how are you going to define success? So these are some of the things that we need to work with you together on to make sure that we tailor your asset management solution to your needs and not just to the general needs. And with that, before we take questions here, we do have a website, which everyone will get a copy of this presentation. And the website is mega.com, cable services. There's an email address to write to us if we don't get to answer your questions today, and also a telephone number. What I did want to say that we do have a calculator on the website that basically just looks for 3 inputs just to get the ball rolling. If you know your budget, if you know your current replacement footage, scope, and if you know your cost per foot, then those 3 variables will help set expectations on how fast you can deal with a solution, how much you can save, how many crew days you can save, how fast reliability is going to come back, and basically everything that you would need to answer. So I do encourage you to take a look at the website. And with that, what I'm going to do is stop right now, and it looks like we're very close to the hour, and we're going to stay on for more questions, but appreciate everybody's attention today.
Awesome. Thanks, Darren. So it looks like at this time we've finished the presentation portion of our webinar. We're going to be diving into a Q&A seminar shortly. We'll now take some of our remaining time to answer those questions as quickly as possible. If you do have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's also a field where you can request a quote or a demo on any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar on June 9th, titled Creating and Modifying Relay Test Management Software Automated Test Modules. All right, well, let's jump into your questions. The first one I have, I'm going to be directing towards Charles Nybeck. Charles, can we measure cable capacitance and tan delta from DAC or DAC?
Thanks for the question, Michael. So damped AC or DAC is a waveform to use for partial discharge testing. So you really wouldn't use it for your tan delta measurement. That would be your 0.1 sinus wave that you would still use for your tan delta measurement. Now, as far as cable capacitance, typically the measurement systems will do a kind of a pre-check of the cable and determine that capacitance. So even in the damped AC mode, you'll still get the capacitance of that cable. But damped AC is typically used to identify and locate partial discharge within a cable. And the idea behind damped AC is you use a DC source and you charge your cable, and there's an inductor or reactor in the cable or inside the test instrument, sorry, and between the cable capacitance and the inductance of that inductor in the test instrument, you have your test frequency, which is likely going to, it's meant to replicate power frequency or your 50, 60 hertz. So it's going to be above that 0.1 hertz that's typically used for your tan delta measurement. So where if you use damped AC, typically again in a partial discharge measurement, you can get the capacitance of the cable, but you will not be able to get the tan delta of the cable. So.
Thanks, Charles. I'm going to send our next question over to Gallo Turan. Gallo, how can I know the VLF voltage test for cables that are not mentioned in IEEE 400.2 Table 3? For example, the maintenance VLF test for a 6 by 10 kV cable rating.
Thank you, Michael, for the questions. If we go and review the IEEE standard 400.2, it define the test voltage and say the voltage levels are based on worldwide practices are from less than 2 U0 to 3 U0, where U0 is the rated RMS phase to ground voltage. And the standard provides a table based on the most normal or common voltage face-to-face designs or manufacturers. When we have these tests, this cable is 610 kV, we need to follow that, depending if this is for the installation acceptance, could be up to 3 times U0. If this is for maintenance, it could be 75% of this. In addition, if we go and review the IEC standard, it doesn't include a table like IEEE does, but it's for cables from 3 to 33 kV, and just mention test this for new cables, test this at 3 times U0.
All right, thank you, Gallo. Our next question is going to be for Charles. Charles, what are the issues if the length of the cable is, say, 20 meters with respect to PD tests for calibration?
All right. So good question there. So when testing a short run of cable, one issue is the capacitance of the cable. As you saw in one of my slides, we had the support capacitor there, so that we can always add capacitance to be able to test shorter runs of cables. So that's not really the limitation. The limitation, though, when you go to test these shorter runs of cables, say 20 meters, is really the localization of the partial discharge. And that's just due to the cable length and the speed at which the signal travels through the cable, and you're really kind of limited. Now you can identify whether or not that cable has PD, but you may have difficulty, or you may not be able to localize that PD within those short runs, and that kind of goes somewhat around the 250 or 270 foot mark on the length of cable to be tested to be able to localize. So you wouldn't really have a limitation as far as determining if there's an issue. You just may have a limitation depending on the localization of said issue.
All right, thank you. Next is over to Leilani Vidal. Leilani, what is the Megger service response time when a quote is requested?
Good question. That is definitely going to depend on the scope of work, but generally a quote will be generated within 48 hours in most cases. Of course, we will be working with our clients on the exact testing that needs to be done, the duration, and so forth. So we'll keep them in the loop of every step of the process.
All right, thank you. Next is back over to Charles. Charles, how long should you wait to perform a tan delta on new cable?
Okay, yeah. So another good question here. So as I mentioned, you don't want to perform tan delta on a new cable just due to those settling chemical processes that can affect your measurement. What I've seen is the recommendation is to wait about 1 year to perform the tan delta measurement, to wait for those processes to settle and subside, so that way they won't influence your dielectric measurement. So after about 1 year of in service, you can perform that tan delta measurement, and that can be your baseline to move for trending, to use for trending in the future when you perform your maintenance testing.
All right, thank you very much. Next is over to Darren. Darren, will the service report include the cost benefit of the recommendations?
Okay, that's a great question. And we can definitely tailor the solution to our customer needs because all customers have different needs. We can even perform, if you want, break-even analysis, discounted cash flow analysis, even if your rehabilitation, I've seen issues where some people will not repair a midspan issue, but they'll repair termination issues. So if you see an issue in the cable midway through the cable, some might repair it with a Dutchman splice. Some might just replace the whole system. The bottom line is, and it's a good question, we can definitely tailor a solution to meet your needs.
All right, thank you, Darren. So to Charles, can tan delta be used to test condition over time for predictive failures?
Yes and no. So tan delta is a very important measurement. It's very vital. It's an integral measurement. It gives you the overall condition assessment of that installation. Now, what I kind of want to highlight here is that one, this is one of the best things that you can trend, right? Because every time you trend that, whether or not the overall insulation is deteriorating, the overall condition of your insulation. So while you can be used to predict failures in that sense, there's also the other aspect of that, which is a limitation of tan delta, which is why we do partial discharge testing, and that is to find the localized issues. And what I mean by that is, if you had a local weak spot in your cable and the rest of your cable was pristine, then your tan delta measurement could reflect to be very good, right? But indeed, you do have a severe defect along that cable, which could lead to a fault failure. So while it can be used for to predict failures, it's more or less to determine the overall condition of that cable's insulation system. Really, you want to use some of the partial discharge testing to determine if there's any localized weak spots. So that's why there's really no one answer fits all here, which is kind of why we showed the different tests, the 3 tests and diagnostic tools, and how all 3 of them give you the complete picture, and you can use 2 of them or so on to complement each other, because that's what they do. They complement each other. So if you run tan delta and get a good measurement, a passing measurement, you can know that the overall condition assessment of that insulation is good. Now, if you run a PD measurement and you find a localized weak spot, that could fail in the near future. And that's the beauty of running both the tests, is having the ability to identify, localize, and fix that issue, and then put that, like brand new cable back in service. So I hope that answered the question. That's why I said yes and no, is because it can, but it's really the overall condition of that cable when you're doing tan delta. So you may miss out on 1 weak spot or 2 weak spots if you have them, depending on, of course, the overall run of the cable.
All right, excellent, thank you. So our next question is a comment from our audience that I know Darren would like to touch down on. So Pranav says, reliability can only be achieved if we do it right the first time. Laying of cables properly is the first step, followed by proper cable terminations. Darren, would you like to touch down on that a little bit more?
Yeah, I mean, Pranav, you're exactly right. This is why we recommend commission and acceptance testing to extend the life, because we know that workmanship is a key detractor to asset life. Absolutely. So, and I think it's a well-known fact, particularly as you see those defects. Charles showed some of them, but I've seen a lot of those predominantly. Obviously, they're basically installational workmanship defects. So, yeah, you're exactly right. Recommending commission and acceptance testing.
All right, excellent. Back to Charles. What about the commonly used high potential testing? Are we abandoning that approach now?
Sorry, I had myself muted there. So no. And I assume by the commonly used high potential testing, the high pot, I assume you mean DC high pot, so I'll answer it on that assumption. So DC high pot was found to be, and this is in the IEEE standard itself, was found to be destructive to the XLPE or plastic cables. So it basically stressed the insulation and could cause cracking and was destructive to the cable. Now, DC high pot is still commonly used on PILT cables where you have the paper, lead, and oil. And the idea is that the oil there is sort of self-regenerative, and the fact that it kind of alleviates some of the stress that would be caused by performing that test on, say, XLPE cable. So we're not abandoning that. It's just for the majority of cable now, the VLF or the withstand testing at 0.1 hertz is kind of the way to go as to not cause any damage to your cable. So still DC high pot's definitely a thing. It's just more predominantly seen on PILT cables.
All right, excellent. Next is over to Gallo. Gallo, how much time would it take to test a segment and in considering the cable length and range?
Well, if we are performing a VLF test, and assuming this is a new cable according to the standard recommendations, this will take like 60 minutes. And this is a H cable, then we probably perform a VLF test in 30 minutes. Something that we can do is sometimes is measure at the same time VLF and partial discharge. So we use the VLF waveform to measure partial discharge. And this is also a very interesting and very powerful information because we are getting more details about how the cable is in the shape of the cable, the condition of the insulation. So a segment, let's say a segment that is 300 feet or 500 feet of a cable, yeah, we can test doing PLF and partial discharging, let's say in 1 hour for a new cable.
Yeah, I'd like to, for an H cable system, I'd like to say that we would like to achieve 6 single-phase tests per day, 4 3-phase per day. There's obviously some delays that can occur, such as weather that we have no control over, but certainly we want to keep efficiency as high as possible as we manage these programs.
All right, excellent. It looks like we've gone a little bit past our hour mark here. I really appreciate you guys sticking around for us. I think that's all the time we have for our Q&A session today, but we know we have a couple questions we'd love to follow up with you offline with. So if we didn't get you to today, keep an eye out later in the week because we will be reaching out to you to work through those with you. But as a reminder, a copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days, although we'll be aiming to have that out tomorrow. But I'd like to thank you all for attending. If you could, please remember to answer our survey when the webinar concludes. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great week.